Hello everyone. So today we're going to be talking about another section in the book. So it's going to be about a concept called rank of a matrix. Hopefully this is legible. For some reason it's coming out a little blurrier than it did last time, but hopefully it looks okay to you. So like with so many things that we've seen in linear algebra, we'll see that even though it seems like we're talking about something new, it's actually going to be stuff that we've already been talking about. So we're basically going to learn some new names for concepts that we are already somewhat familiar with, and then use those new concepts or new names to come up with a pretty nice result that relates some different aspects of matrices. So I want to give you a warm-up problem, and I would encourage you to try this yourself first, although, I'm going to go through it in actually a good amount of detail just because I think by looking at this example carefully, it will help us kind of understand the next part. So I would still encourage you to try it yourself first, but then I would still watch this next part of me explaining it just because I think I'll point out some things that you probably want to be noticing. So I'm going to write down a matrix. So it's going to be, let's see, a 3 by 5 matrix. So 3, 6, negative 1, 1, negative 7, 1, negative 2, 2, 3, negative 1, and then 2, negative 4, 5, 8. And I'm sorry, my hand, so I don't know if you've ever seen, but some people have they make these like special gloves you can wear while doing using a tablet, because otherwise your hand while you're writing kind of like makes straight marks. So I'm sure that's going to keep happening because I don't have one of those fancy gloves. So sorry about that. Okay, so let's say that this is our matrix, and let's say that this can be reduced to using row operations. An echelon form matrix, and the echelon form is going to be 1, negative 2, 0, negative 1, 3, 0, 0, 1, 2, negative 2, and then the last row is all zeros. Okay, so the question here is going to be to find the dimensions of the column space and the null space of A. So along the way, we're going to also actually explicitly find the column and null space, but the question that we're eventually going to be focusing on is the dimensions. So we want to find the dimension of the column space of A, as well as the dimension of the null space of A. Okay, so let's start with the column space. Oops. So one thing that we talked about in the past was that when you're trying to find a basis for the column space, and of course, if we're looking for dimension, we want to find the basis, right? Because that's what tells us the dimension. So we discussed in the past that a basis for the column space is the set of pivot columns of the matrix. So I just want to quickly remind you why that is. So let me first write that fact down. So the pivot columns of a matrix A form a basis for the column space of A. So I think it's easiest to see why that is when you look at a matrix that's already in echelon form, and especially reduced echelon form. So I want to first kind of point out what's going on by looking at U, and then once we understand what's going on with U, then we'll explain why it still is true that those same columns of A are a basis. So if you look at our matrix U, we can see that the pivot columns are the first column, the third column, and that's it. Those are the only two pivot columns because our only two pivots here are 1 and 1 that appear in those two columns. So the reason that we can see that those are a basis for the column space of U, so right now we're just focusing on the echelon form matrix, is that they're really the only columns where any new information is added, right? If you look at like the second column, it doesn't have anything new compared to the first column. It still only has an entry in the first position. And then if you look at the third column, that's where we introduce a new position. And so that introduces new information. And so because the pivot columns are the columns where we're kind of adding in this new entry, everything else is going to be able to be written as a linear combination of those two columns. So hopefully that can convince you that, at least for you, that the two columns that I've highlighted are a basis for you. And then the reason that we can still kind of focus on those same columns in A, so the first column and the third column, even though they're different in A, those are still going to be the pivot columns of A. And so the reason for that is that if you were to solve, so let me think of how I want to write this down. I wrote a bunch of stuff on my notes, but it's a little longer than what I want to write on the screen. So let me think for a second. So basically, I'll just put this in parentheses because it's kind of a side note, but the relationship amongst, I don't really know the difference between the word among and amongst, but I'm just going to go with it. The relationship amongst the columns of A is the same as the relationship amongst the columns of U. And the reason for that is that basically a dependence relation is one way of expressing the relationship amongst the columns. It's really kind of the right way of expressing a relationship amongst the columns. And remember, the way that you find a dependence relation is by solving the homogeneous system of equations. So if you were to solve AX equals 0, that's going to have the same exact solutions as if you were going to solve UX is equal to 0. So think about why that's true. It is true, and the reason is basically that your vector x is representing the weights that you're applying to each of the columns. So whatever you find for x, that's telling you the relationship between the columns. And so whatever that relationship is, you're going to get the same relationship in the reduced form, because just picturing like what it would look like to make the augmented matrix and go through this reduction, that column of zeros is going to stay the same. So the solution set is going to stay the same, and the solution set is what tells you the relationship amongst these columns. Okay, so hopefully I've at least somewhat convinced you that the columns that I highlighted in A are a basis for A. So let's write that fact down. So if we were to make the set -3, 1, 2, and -1, 2, 5, that set is a basis for the column space of A. And so therefore, we can say that the dimension of the column space of A is equal to 2, because we have 2 basis elements. Okay, I realize I think I did this differently than I intended to. Let's see. Which layer did I write on? Okay, perfect. I'm trying to set something up so I can like easily kind of turn on and off the different things that I wrote. And now I messed it up. Where'd it go? I'm just very confused. I'm sorry. Now I lost I lost the thing that I had just written. I'm very confused about that. It's like, it seems like it's on layer 7. Okay, let's just say it's on layer 7. Sorry about that. All right, let's do the same thing now for the null space. So I'm actually gonna have to rewrite. Oh my gosh. Apparently still have not quite figured this out. So I'm going to rewrite down this matrix and its reduced form. I probably could have found a better way to do this so that I didn't have to rewrite it, but it'll just be nice if we can still refer to it. So this was positive 6, negative 1, 1, negative 7. Feel free to fast forward through this part of the video. Okay, so that was our original matrix. Here's all this stuff from my hand. And then the reduced form was 1, negative 2, 0, negative 1, 3, 0, 0, 1, 2, negative 2. And by the way, so if you did the worksheet from yesterday, there was the last question that I put on the worksheet is really similar to this question. So maybe you've already got some practice with this. Okay, so let's talk about finding the null space. And specifically, we're going to be eventually finding the dimension of the null space. So finding the null space basically boils down to solving a homogeneous system of equations, right? So to find the null space, we want to solve AX is equal to 0, right? Because that will tell us what are the vectors that when you multiply them with A, you get 0. That's what the null space means. But as we already just discussed earlier, that has the same solutions as if we were to use the reduced form. So that means that we can just jump right in with our reduced matrix and make it an augmented matrix and use that to read off what the different solutions are going to be. So I'm just adding a column of zeros because we're looking at a homogeneous system of equations. Okay. So when we go to write down what's going on here, you know, sometimes the first step you want to do is basically identify what are your free variables. So the thing I want to point out here is that where are the free variables coming from? They're coming from the non-pivot columns of your matrix, right? So I'm just going to go up on the original matrix or on the matrix U and circle the columns that are going to correspond to free variables. Because those are non-pivot columns are going to be free variables, and so that means that x1 and x3, which are the variables that are not free, those ones are going to be expressed in terms of x2, x4, and x5. So let's write that down. So the free variables are going to be x2, x4, and x5. And so we can write x1, if we were to solve out that or express the first row of the matrix as an equation and solve it for x1, we'd have x1 is equal to 2x2 plus x4. I wrote something down here that I think is wrong. So let's see. 2x2 plus x4 minus 3x5. For some reason I didn't write the minus 3 on my notes. And then we can write down x3, that's the other pivot column, the third column. So we can write that one down as negative 2x4 plus 2x5. So what that means is that now when we go and write out the solution vector, so we have x1, x2, x3, x4, x5, we can write it in this parametric vector form. That will allow us to now see what the basis is for our null space. So we can write this as, so the first row will be 2x2 plus x4 minus 3x5. The next one is x2 is a free variable, so that will just be x2. Next one will be negative 3x4 plus 2x5. x4 is a free variable, x5 is a free variable. Okay, so now we can pull out those free variables and everything else will be expressed in terms of them. So we can do x2, and that will leave us with 2 from the first row, 1 from the second row. Oops. Sorry about that. Let me scroll back over. Third row will be 0, fourth row will be 0, fifth row will be 0. And then we have x4, and that's going to give us 1, and then 0, and then negative 2, and then 1 and 0. And then our last one will be x5, and that will give us a negative 3 in the first component, 0, 2, 0, 1. So basically what this tells us is that those three vectors we found, so what we just wrote down here is a linear combination of three vectors, right? So x2, x4, and x5 represent any real numbers. And so that means that the column space is equal to the span of these three vectors. And these three vectors are linearly independent. And I don't really want to get into it, but basically whenever you do this, this approach of finding the parametric vector form, the vectors you find are just always going to be linearly independent. In this case, you can kind of tell just by comparing them, you can see that there's no way to combine two of them to get a third one. So what we can say now is that basically these three vectors, 2, 1, 0, 0, 0, 1, 0, negative 2, 1, 0, and negative 3, 0, 2, 0, 1. This set of three vectors is a basis for the null space of A. And so therefore we can say that the dimension of the null space of A is equal to 3, because we had three basis vectors. Okay. So I want to introduce a couple of new words that will then let us talk about this next stuff a little bit more easily. So let me see if I can this time get it right in terms of going to another page. Oh my gosh. My pen is just like suddenly not working. Okay. Okay, hopefully this will work. So some new, let me do a new color for our new terms. Let's do purple. So some new terms. So the first one is the word rank. So the rank of a matrix A, which can be written as rank A, is the dimension of the column space of A. So I'm going to write that in our kind of abbreviated way, but it's just the dimension of the column space of A. And so basically it's an important enough concept that rather than have to write dimension of column of A, we can say rank of A instead. So just to give an example, the example that we just did, so the matrix that we were working with previously, we found that the column space had 2 vectors as its basis, and so the dimension was 2, and so you'd say the rank of that matrix is 2. The other word, and so your book actually doesn't, this is a commonly used word, but for some reason your book doesn't have it, but I'm going to use it anyway. So the nullity of a matrix A, which we can just write as, I probably didn't have to write this, it's kind of obvious, it's not really an abbreviation, nullity A, that's going to be the dimension of the null space. So for example, in our previous example, the null space that we just did had a dimension of 3, and so we could say that the nullity of that matrix is 3. So the important distinction here, though, I think the one place where you can get confused is keeping track of what kinds of objects you're talking about. So when you're talking about rank or nullity, that's a number. The rank of a matrix is just a number. The nullity of a matrix is just a number. When you're talking about the column space or the null space, then you're talking about a set of vectors. Similarly, if you're talking about the basis of the null or column space, that's a set of vectors. But as soon as you say the word nullity or rank, you're not really talking about a set of vectors, you're just referring to a number. It's like a property of a particular matrix. So based on what we saw, and actually I'm gonna, hopefully this isn't a mistake, but I'm gonna try to go back to the first page, here we go. So notice that when we were working with this, this example, so we found that the pivot columns were a basis for the column space. And then it ended up being that the non-pivot columns, they weren't a basis for the null space, but they did tell us how many free variables there were. And then the number of free variables is what told us the dimension, right? Because I'll flip back to that page in a second, but basically we have, the 2 columns that are highlighted in orange, those are the ones that were pivot columns. The 3 columns highlighted in pink were the ones that were non-pivot columns. And so basically the columns that are highlighted in pink, that's the ones corresponding to x2, x4, and x5, those ended up being the free variables. So if we look back at this example, we have 3 free variables, x2, x4, and x5, and that's why we ended up with dimension 3, because there were 3 free variables that gave us 3 vectors. And so it turns out that that is always going to be the case. So in general, sorry, oh my gosh. So in general, hopefully this pink isn't too bright. The rank of a matrix A is always going to be equal to the number of pivot columns. So this is just what we saw in our last example. And then the nullity of that matrix is going to be equal to the number of non-pivot columns. And I want to be really clear that the non-pivot columns, those columns themselves did not form a basis for the null space, right? Because the basis of the null space had vectors that had like 5 components, I think, right? 5, and whereas the original matrix only had 3 components in each column. So it's not that the non-pivot columns actually form the basis, it's just that the number of non-pivot columns corresponds to the number of free variables, and that will correspond to the number of basis elements in the null space, of the null space. So something you might notice here is that, well, if you take the number of non-pivot columns and you add up the number of pivot columns, that's going to give you the total number of columns of the matrix. So I'll write that out, and then that will lead us to an important theorem that's called the rank nullity theorem. So what I'm going to write is going to be probably kind of obvious, but the number of non-pivot columns of a matrix plus the number of pivot columns, I guess I should have written this in the opposite order to match up with what's above, that's okay. So if you add up the number of non-pivot columns, number of pivot columns, that's going to give you the total number of columns of a matrix. And so that basically gives us a relationship between the rank and the nullity of a matrix. And that's what we'll write down in a second, is what's called the rank nullity theorem. So the rank nullity theorem says that for any matrix A, the sum of the rank and the nullity is going to be the same as the total number of columns. So I'll switch colors because this is an important theorem. So the rank nullity theorem. In your book, they just call it the rank theorem because they don't use the word nullity. But the rank nullity theorem says that if A is an m by n matrix, so remember when you say m by n, m is the number of rows, n is the number of columns of the matrix. So if A is an m by n matrix, then if you add up the rank of a matrix A, and then you add to that the nullity of that same matrix A, the total is always going to be equal to that total number of columns. So I want to do a few examples with this and give you kind of an idea, hopefully, of like kind of a different way of thinking of this in terms of linear transformations. So let me open up a new page. Okay, so for example, now that we have the rank nullity theorem, we can answer a question like this. So let's say A is a 7 by 9 matrix whose, I guess whose is kind of a funny word to use for a matrix, but that's okay, whose null space has dimension 2. And so the question is, what is the span, or sorry, what is the dimension of the span of its columns? So this is basically a direct question of applying the rank nullity theorem. So the rank nullity theorem tells us that we want to look at the total number of columns in our matrix, so that's 9, and that number is going to tell us the sum of the rank and the nullity. So it tells us the null space has dimension 2, so that means that the nullity of this matrix is 2, and then we want to figure out what is the rank, because the rank, that's what they're asking, right? They're saying, what's the dimension of the span of the columns? That's the same as the rank. And we know that the rank plus the nullity, or sorry, rank of A, not rank of 2, is supposed to add up to the number of columns, which is 9. And so from that, we can conclude that the rank has to be 7. So what that tells us is that this matrix, we don't know anything really about this matrix. We don't know what the actual columns or rows look like, but we do know that the span of the columns is 7-dimensional. Okay, let's do another example. So, sorry, I'm just trying to switch back to my other color. So let's say now instead that A is a 7 by 9 matrix. Actually, maybe I'll switch this up. Let me think for a second. Yeah, let me switch this up to make this question work. So let's say A is now a 9 by 7, so it means it has 9 rows, 7 columns. and let's say that all of the columns of A are linearly independent. And so the question is, basically, I'll just write it more simply this time. I'll just say, what is going to be the rank of A? So last time I said, what is the dimension of the span of the columns? The whole point of introducing the word rank is so that we don't have to write all that stuff out. Okay, so in this case, we know that our sum of our rank and nullity is going to be 7, right? But this one has a slightly different kind of presentation of the information. So it tells us that the columns of A are linearly independent. So we have to think about what that tells us about the nullity. So remember that if a matrix has linearly independent columns, that means that the homogeneous equation AX equals 0 has only one solution. So if the columns are linearly independent, that implies that AX equals 0 has only the trivial solution. And if AX equals 0 has only the trivial solution, that means that the dimension of the null space is 0. So maybe let me write out another step on the way to that. So if AX equals 0 has only a trivial solution, that means that the null space of A is just the 0 vector. There's no other vectors that you can multiply with A to get 0. And so the dimension of a set just containing the 0 vector we've mentioned before is 0. It's tempting to think it's 1, but it's not, it's 0. So one-dimensional subspace would be the span of one non-zero vector. Two-dimensional is the span of two non-zero vectors. Here now we have just the 0 vector, so the dimension is 0. And so this tells us that the nullity of this matrix is 0. And so therefore we have rank A plus nullity of A in this case is equal to 7. So now we know nullity of A is 0, so in this case that implies that the rank of A is equal to 7. So what you might notice here is that there's some kind of like push and pull between the nullity and the rank, and I want to kind of summarize that in our next example, and that will be kind of the last thing we talk about today.